I've got the pleasure of introducing Von Kimmel. He's an associate professor at Technion in Israel, so he came all the way to Canada to give this talk. In fact, he's giving another talk on Monday, so if people are around, he's giving a talk in the computational math seminar series, or colloquium series, Monday 3:30, I believe. I think it's 3:30, but you can see online. He got his PhD from Technion. Spent some time away from Technion. He spent 3 years doing a postdoc at, correct me if any of this is wrong, 3 years doing a postdoc at Berkeley. Also spent some time at Stanford. But I first met him in 2003 at a conference in Washington, D.C., where he gave not a talk, but a talk in a session on PDEs as applied to image processing. And I really enjoyed it. I thought it was exciting work. And he was a good speaker, so I invited him. Let's see what else. He's won many awards. You can read it all here in his bio. And he's written a book on numerical geometry of images. No, really, he's written a book, Numerical Geometry of Images. I think I'm going to get him to sign my copy later today, if he's willing. And a colleague of mine happened to mention that his name means rye bread in Yiddish. So welcome. I'm honored to introduce Von Kimmel.
Thank you. Okay, thank you for the very nice introduction, and thank you for inviting me here. Okay, so in the black booklet that you have 2 talks of mine. I'm going to talk only about the first half of it because I will not be able to rush through everything. However, at the end, I will give you a glimpse, or call it a teaser, of what I'm going to talk about on Monday here. So what is numerical geometry of images? First of all, the power that we are using are our graduate students. Today I will focus on works of Roman Goldenberg, Michal Holtzman-Gazit, and Alon Spira. And on Monday I will focus on research topics of the rest of my students. I also have many colleagues, Freddie Brookstein, Laurent Cohen, Vicente Cáceres, Nachum Kiryati, Ud Rivlin, Guillermo Sapiro from Minnesota, probably also heard him at the same seminar, James Sethian from UC Berkeley, Nir Sochen and Irad Yavne. And when we are talking about numerical geometry is my interpretation, is my name for a set of problems that you can solve practically in a sense. So it's not like computational geometry in which you are looking for a bound on how complex the problem is, but rather you have the problem, solve it in the most efficient way. We draw tools mainly from the fields of numerical analysis and differential geometry, calculus of variations. And let me give you, in this talk, I will give some examples, and I apologize for the fact that you will see some equations. Up until now, we haven't seen much of equations, but probably except Professor Grenender talk, where we have seen some, but I will try to give the geometric flavor behind these equations. So first of all, now I will talk about low-level image computer vision problems, and from there you will be able to extract relevance to problems in medical imaging. And the first thing that people mentioned Schrödinger in the 20s. The first thing that physicists tried to do when they went into the field of image analysis or physics of images is try to represent our color perception as a geometric structure. So this is true from Helmholtz starting in, we have a pointer here, starting obviously more than 100 years ago, and follows through a lot of other physicists, including Schrödinger. And the question was, how should we represent the color space? So you can think about our perception as being Euclidean, for example. You add the distance in red, green, and blue, and the further you depart from a specific color, then this is how you perceive it. However, and people invented these strange arc lengths in color space, Euclidean, more sophisticated, and even more sophisticated. And actually, Helmholtz said that, claimed that he invented the whole Riemannian geometry even before Riemann. The issue is that once you define an arc length for color perception, you need, and you would like to apply some image processing tasks, you need to combine it with space. Well, you need to average every point with its neighbor, say. So the first problem that I will describe is merging these two distances together. So we have the distance in the image plane, as well as the distance in the color domain, say the Euclidean distance in the color domain. And if you would like to measure distances on the color image, then we combine both of them together with some coefficient that determine the ratio between spatial and call it spectral quantities. So what can you do with such understanding? You can do many things. For example, you can fill in the missing colors in a classical problem which is the mosaicing. If you think about color formation, and you perceive this idea of using the image as a surface, then you can take the raw image of most of the modern sensors, most of the modern digital cameras, and fill in the missing colors. Well, each camera has at each and every point one sensor that corresponds to one color. In order to see a color image, a full color image, you need to fill in the missing pixels. So here, for example, at this point, we have just blue. So we have to interpolate somehow the red and the red and the green. And the trick to do that is to use some understanding, some meaningful model about image formation, as well as the concept of images as surfaces. And then you can do magics like that. If you just do linear or kind of linear interpolators, you get these aliasing effects. If you zoom in, you can see these effects when you fill in the missing points. Well, if you use more sophisticated model-based techniques, you get rid of these effects. Again, you can see these effects here along the eyebrow of this person. So when I'm saying considering the images as a surface, and I think about U of x and y as the image, then the most natural measure in an image is the area. Well, after length, if we have length, then we can define area. So assume that you compute the area, which is the x squared plus the y squared plus the d intensity square, and this is your area, and this is some integral measure that you are measuring. Well, you actually measure the integration over the metric of the image, and you take the first variation with respect to this measure. Then what you get is a heat equation. But, well, now you use it as a gradient in the gradient descent process, so you get a heat equation, but the heat equation acts according to the metric of the image. If you apply this heat equation on the image, then you will get information disappearing in a gradual way. I will give the geometric interpretation of this heat equation in a while. But you can see that edges are preserved in a sense, and you selectively smooth the image. In color image, it makes more sense, even more sense. Now, this is just a schematic writing. Obviously, the metric does not look exactly like that, but I just wrote it as some sort. So this is the arc length, and from there you extract the metric. So if you minimize the metric of the image, then again, information disappears in a gradual way. Now we have a system of equations, and you can see that, again, you smooth away the perturbations, the geometric perturbation at each and every color. However, the edges between the colors are somewhat preserved. Why does it happen? Let me give a very simple explanation to why it happens. If we look at the regular heat equation, and we get some initial condition that we feed into this equation, then what practically happens is that the solution at time t is equal to a convolution of this initial condition with a Gaussian. So if this is the initial condition, you run a Gaussian on this, along this axis, and each and every point is averaged with respect to its neighbors, and eventually you get something like that. It has good properties because it eliminates the high-frequency geometric noise, or noise. Well, Gaussian in space is also Gaussian in frequency, so it's a low-pass filter in a sense. However, the bad effect on images is that it smears the edges. What would we like to do? What we would like to do is to define some other operator. So if we minimize the area of the image, what we get is the following operator. And this is exactly the same heat equation. However, think about this Gaussian, which is now being plotted on the signal itself. So the support of the Gaussian would be the signal itself. Now, as long as the Gaussian is moving along a flat domain, its support is well, it averages its value with its neighbors, with its correct neighbors, and everything is fine. It creates a smooth region. However, when it approaches an edge, the tail of this Gaussian has to travel a very long distance, and the influence of this Gaussian is losing its effect, and therefore the edges are preserved in some sense. So together with Nir Sochen and Ravi Maladi, we realized this fact, and then we published several more papers about this. And in order to apply this efficiently on color images, what we can do is we can actually compute the short-time kernels, which are very interesting, and apply them onto the image. Now, a different branch of filters that emerged recently, actually rediscovered recently, it started, I think, with Tomasi and Manducci, is bilateral filters. Bilateral filters do more or less the same. However, instead of interpolating, instead of measuring the distance along the signal, it just shoots the distance. So this point, when it is averaged with this point, there is just a straight line along this direction. And there is also a new development that that was introduced by Jean-Michel Morel and his student, in which they actually allow a very small, well, they actually eliminate altogether the values along the x direction and do it in some other scale. And practically what they do is they, in order to denoise part of the image, they look at a patch and they search for a similar patch all around the image. And then if they found a similar patch, then they average the two. So it's all related to this kind of PDEs in various scales. Now, let me go back to probably the most basic and most simple operator that one can think of when thinking about image analysis. This is edge detector. So what is edge detection? Edge detection is the process of finding and labeling the location in the image where gray level rate is changing. So the output of this process is some sort of edgelets or edgels. And the second process of edge integration is tiling all these small pieces into something meaningful, which is called the image boundary. And we call it edge integration. The classical edge detectors are Sobel, Pruitt, and others. If you'll just run MATLAB and run edge, you will see all of them. And they all look for the change some change in the intensity. Now, if you look for a change in the intensity, what you really want to do is to look for the local maximum of the derivative of this function. Okay, so you take the derivative of this function, and in order to look to locate accurately this local maximum, what you take is the second derivative and look for the zero crossing of the second derivative. So the zero crossing of the second derivative, or it's called zero crossings of Laplacian, it's called the Mar-and-Hilbert edge detector, is a sort of an edge indicator function. Now, Haralick and later on Kenny and others demonstrated that if you look at only at this component, well, think about the image and imagine these as the level sets of the image. So these are the equal height contour of the image. If you take the second derivative only along the gradient direction, then you get better localization of the edges. And this is what is known today as the Kenny edge detector. It should be named Haralick because Haralick proposed it first. And I will give you along this talk a variational explanation of why this works, or why this works better than the Mar-and-Hilbert edge detector. The zero crossings of the Laplacian works, but it's more sensitive to noise, for example. And then comes the second chapter, which is edge integration, and I will show how I can put this kind of edge detector into the process of edge integration and put everything into one framework. So it's not so new, but a popular new wave for doing segmentation is taking the image. It's called geometric active controls. If you will search it in Google Scholar, you will find about, I don't know, 600 citations to this work. I don't consider it as well, at least it's the most popular work for some reason. So the trick is like that. You take the image, and then you take the gradient value of this image, okay, and you get something like that, where 1 over the gradient magnitude is plotted here. And then the question is, throw curves on this image so that the curves minimize the integration along this G function. So think about this image as in some topographical way in which blacks have low values. So you try to put curves along this image so that these curves go mainly along the dark regions. Okay, and this would integrate these. Let's call this edge integration function. This will integrate these edges into meaningful curves, boundaries between objects. Eventually, what we would like to do is to, well, I'm sure that most of you have seen, who haven't seen this picture before? Okay, so there is a Dalmatian dog here, a Dalmatian here. Can you see it? Okay, so there is no trick here. What we would like to do is apply the same trick or apply automatic machinery in order to isolate the boundary of this embryo within ultrasound image. So we first of all circle the embryo with some curves, and then we allow the image to take these curves into the local minimum, and eventually we segment this embryo out of the background. Again, here we, for example, apply our knowledge, our prior knowledge of water horses in order to isolate these ponies out of the background. Here, for example, this is a famous picture in which we have, well, can you see something strange about this image? Faces. Okay, so there are 13 faces. Now you know what faces are, so if I also give you some hint about these faces, like where they are, then you can really see them and really isolate them from the background. So prior knowledge is good. However, in some cases, good prior can actually mislead us, and this is a classic example. Probably most of you have seen this before. This is the same baby after a while. And this is obviously a pacifier. A strange design for a pacifier. So priors are important. However, we should be careful about priors because they can mislead us and lead us into wrong conclusions about what we see. Yet another example, probably you've seen that. You know what? You know how the face of the girlfriend of this guy looked like? So probably you could have imagined. So again, priors can mislead us. What's the relevance of it? Well, I consider now priors as initial conditions. For example, if I circle these objects and minimize the edge integration function along this curve and allow the Euler-Lagrange take this curve as a gradient descent process, then eventually I can isolate this object out of the background. Of course, we implement this equation in a Leveset's method using the Osheshetyan method because it's very stable. And if you look for implementations of it, you can find it at the back, at the last page of this book. There is a solution to some problems, and those of you who try to solve the problems will probably get into it. You need to switch one procedure, and then you get this kind of implementations. So the source code in MATLAB is there. If you can do it in still images, we can also extend it to surfaces, in which case the edge integration function is nothing more but the gradient magnitude in x, y, and z. And then the curvature now is the mean curvature, and the rest is the same. So we can isolate, for example, this tumor in this three-dimensional medical information. Of course, if we do it on gated CT, then we can do it in 4D. After 4D, curse of dimensionality hits you, so we can do reconstruction of just a 3D. Well, here it's 2D manifold and the 4D manifold, which is the beating heart in time. After 4 dimensions, curse of dimensionality hits you, and you can't really process this 5-dimensional data. The connectivity is too intensive, so 4D is the max that you can probably do and enjoy this level set method. We can, for example, use time. So here the edges are, we also look for gradient in time. So then we can track this object, this cat. And we were not so pleased with what we have seen here. We knew that there is more information and we can actually go very tight to the boundary of this cat. So we try. So something was missing. In order, for example, to understand what we see here, we see a blob. So a blob of a cat and a blob of a dog would look very similar. Of course, after animal trials, we move into humans. For these kind of experiments, you don't need any to sign anything. So again, you can see the blob circling this person, and again, we were not so pleased with these results. If you would like to do image analysis on these results, it's a problem. What was missing? If we go back into the images that we were processing, we were looking at the gradient magnitude, just the magnitude of the gradient. But there is something else here, the gradient direction. If we, for example, zoom in into this image, then besides magnitude of the gradient, there is a direction at each and every place. So we go back to the drawing board and we ask the following question. Say that I would like to find edges. What should I look for? So, of course, I should look for the places along which the gradient has a big magnitude. However, I would also like my estimated curve to align, well, I would like the normal of this curve to align with the gradient direction. So I know that my curve, that my edge here, should be something like that. Why? Because the normal should align with these directions. If we write it formally, then this is a curve, and this is a gradient vector field. I would like the angle between the normal to the curve and this gradient vector field to be maximum. Well, I would like the cosine to be as large as possible. Okay? So I would like this angle to be as small as possible. So we can define the following measure. Obviously, there should be some absolute value here. I would like to project the normal of the curve onto the gradient direction, and I would like to maximize this measure. If I go back to my basic calculus books, then I see that there is a simple integral here. There is a dot product between a normal of a curve and a vector field. So what I basically look for is I apply Green theorem, and eventually what I get is that is the following equivalence, which tells me that I would like to maximize integration over some scalar function, and this scalar function is nothing but the Laplacian. So I would like to maximize this integration over the Laplacian. Now, if you integrate over some scalar function, and the scalar function can get positive and negative values, and you would like to accumulate as much as positive values as you can, then what you're really looking for are the zero crossings of the Laplacian. Okay? So this is yet another variational explanation for the Mara and Hilbert edge detector. What Mara and Hilbert did, without saying it explicitly, is solving the following problem. Look for a curve that best aligns with the gradient vector field. So, okay, so we have an explanation for the Mara and Hilbert edge detector. However, the Canny edge detector is better. And we asked the following question. Why is the Canny edge detector better? So let's go back to the drawing board. Okay, so what is the Canny edge detector? If I zoom in onto this image, and I plot one level set of this image, one equal height contour of this image, then I have the gradient direction, and I have the tangent direction. Okay? Now, the Laplacian is a rotationally invariant operator, so I can write it as a second derivative along the x and y direction. However, I can choose local coordinate system, and specifically the gradient direction and its dual, and write the Laplacian as follows. So, in other words, I can express the second derivative along the gradient as the difference between the Laplacian and the second derivative along the tangent. Now, why did they did all these mathematical exercises? The reason is simple. For that, we already have a variational explanation. We know that this is the alignment term. This is the term that tells the gradient to align with the normal of the curve. But this is a very simple and nice geometrical structure. We call it topological homogeneity. I will write it differently. And this is the most complicated slide, the most complicated mathematical slide that you will see here. Afterwards, everything would be smooth. And how long do I have?
Sorry, let me check.
So the answer will come up in a few seconds. Okay, so this is the Ix6c, which is the second order derivative along the gradient direction. And this is how we write it. And if we write the equation, then using the co-area equation, what we have is that we integrate the curvature of the level sets along closed contours and along the intensity direction. So what the co-area equation actually translates me from the x and y integration to arc length and intensity integration. And integration over curvature is 2 pi. So what we have is something which is called Minkowski functional, and it's and Cronrod measure, and it's an extension of the total variation to 2-dimensional domains. 1130. Okay, thank you. So we have 2 pi, which is a constant, times the intensity. Okay. So if I have one hill, then this measure will actually measure the height of this hill. If I have 2 hills, then it will measure the height of one hill, and from the saddle, the height of the second hill. I saw that the last talk, there is a talk about the Montanese theorem that relates to, well, let's leave it aside for a moment. So we have a measure of how complicated the topology inside the curve is. So again, this term minimizes or maximizes the alignment, and this term minimizes the minimizes the unhomogeneity inside the curve. So these two measures compete with one another, and therefore Ix6c is better than, in a sense, the just using the Laplacian. So now we know that. The question then is, can we design new edge detectors which will be better than the Canny or the Haralick edge detector? And the answer is obviously yes. Once you know which functional produces this edge detector, you can design new ones that are better fitted to the problem that you have in hand. Some interesting comments. This Ix6c is also denoted as infinity Laplacian. And in 98, Casalas, Morel, and Sebert showed an axiomatic interpolation method in which they solved the following equation. So it's not the Laplace equation, but just taking the second order derivative along the gradient, and it's a very nice, the axiomatic means that they write a set of axioms, and eventually the output is that this is what you have to solve in order to interpolate images if you have missing data. It then gave birth to in-painting methods and other techniques. So what do? We use this alignment term and couple it with nothing else but the geodesic active contour measure. So if we couple, and the geodesic active contour measure is used mainly for regularization. So if we couple these two measures, if we just use the geodesic active contour in order to segment these objects, then we see these over-smoothing effects over here. If we just use the Laplacian zero crossings, it tends to be too sensitive to high-frequency noise. If we couple them, then we can do a better job. You can also do it for open contours, in which case you have to derive the dynamics at the end of these contours. And here we don't use level sets in order to implement it. So what is the list of operators that I've shown you so far? We have seen the weighted arc length or the geodesic active contour measure. We have seen weighted area, okay, which actually, well, we haven't seen, but I can tell you that weighted area is just the weight time the normal. We have seen the alignment term, which is the Maran-Hilbert edge detector. and we put all of them together, and what we get right now is something that needs some additional terms. So we were lucky that Chan and Veze pointed out that if you simplify the Mumford-Chia functional, which is also used by Zhu and Yule, and it goes back to Max Lloyd and all the regularization, vector quantization technique that you are looking for. And I gave you very complicated words to a very simple notion, which is if you want to segment something, threshold. Why threshold? Why threshold? Let's look at the following function. Well, let's look at the following image. Say that I would like to segment these two objects from the background. Then what I'm basically looking for is some set that would separate the interior of this object from the exterior of this object. So I'm looking for a constant that would represent the interior of this object, which is measured here, and a second constant, C2, that would represent the background. Now, these two constants are competing with one another. Probably you've heard about, so these two constants are competing with one another. The first constant is the average inside the contour. The second constant is the average outside the contour. And the contour itself, or the Euler-Lagrange equation of this equation, is nothing but the location in which the image is equal to the average between the two, which is thresholding. You have a number inside, you have a number outside. Thresholding is the average between the two. Okay? So this is yet another variational explanation to thresholding. What is the advantage of it? The advantage of it is that now we can couple it with the previous measures that I've shown you, with these ones. And I can also start playing with the metric here. Instead of the L2, I can do L1. L1 gives me nothing. The main difference is that instead of averaging, I take the median inside. So if I have a very noisy object, the median would be more robust. Okay? So we put everything together, and now we try to segment the images that I've shown you before. So we take new students, and now we can really go around the boundary of this object. So again, after human trials, we move into animal trials. And again, you can see that the object is really, the boundary of this object is really isolating the object. And again, in order to not discriminate, we apply it to dogs. And again, this is here you will see the boundary of this dog when it walks. So now we have, and we recorded many dogs and many cats and a few people. And now we wanted to apply recognition to these objects. So first of all, what we did, let me freeze it a little bit. First of all, what we did is we took all the silhouettes of all the people and all the silhouettes of all the animals, and we created two libraries. Now, if you have a new silhouette, then you try to project them on each of these libraries and find the best match. Now, this is an exhaustive procedure. So what you do is you apply SVD to the first library and SVD to the second library, and then you have silhouettes, you call it. And the projection is much simpler. You just project it onto the first, 10 or 20, and the one that gets you better alignment is the selected family of objects. So when I'm trying to project this silhouette onto the set of animal basis, first 20 or something like that, I get this garbage. However, when I try to, and again, we center each and every object, and we align it, in some sense. When I'm trying to project it into the set of people, then I get something that reacts better, and so I can say that this silhouette belongs to a person rather than a cat or a dog. The next thing is to try to understand periodic motions, and we did something similar. So we have a periodic motion of a walking dog, a running dog, and a galloping dog. We take a period and we normalize it to about 10 frames. We project each and every silhouette to its own library, and now we plot the curve of these projections, and we do the matching. So it's the simplest classification procedure that you can think of. It's a linear classification that can actually take all these, and then we apply multidimensional scaling, and then we see that all the walking dogs are around here, all the cats are here, etc., etc. So it's a relatively simple classification technique. And again, moving to human trials, we can differentiate between a walking person, running person, and a person that runs diagonally towards the camera. So this is the embedding into this Euclidean space, which is done through multidimensional scaling. Again, apply MDS. MDS is now a standard procedure in MATLAB. Okay, now we move into the medical world. What happens if we would like, for example, to isolate the cortex, okay, the envelope of the cortex, or the gray matter? We can train, what we have done is we trained two surfaces. One of them that captures the difference between the gray matter and the fluids that surround it, and the other one that is characterized by the change between the gray matter and the white matter. And we also tell these two surfaces that they should be about 3 millimeters one from the other. So we have these extra terms here, and here instead of curve I'm writing it in a implicit form. So this is a level set form. Now we let these two surfaces move, and eventually one captures the boundary between the gray matter and the rest of the fluids, and the other one between the gray matter and the white matter. And you can see these renderings of the surfaces. The data that we had is not as nice looking as the data that we have seen in the previous lecture. However, it produces interesting results. And we can also apply it for segmenting thin structures in three-dimensional data sets. And this is a joint work with two physicians. This is a work by Michal Holtzman-Gazit with Dorit Golsher and Nati Peled. And the idea is to separate these thin structure, these arteries from the background. Now, have it been used in real applications? The answer is yes. I know that Philips used a software by Thomas Deschamps, who implemented some of these techniques and extended them to isolate in some of their products. Mediguide is a small Israeli company that is doing position and orientation, and they have been able to put position and orientation in front of an IVUS, intravascular ultrasound. So you have this very tiny ultrasound that goes into the arteries, and it rotates in about, 60 times a second, and gives you sections of the artery as you go along. So the issue is that the companies that are manufacturing these very tiny IVUSs can't really push them, because you need to be really an expert to read these images. So what Mediguide did is they did an automatic segmentation method that, besides position and orientation, it also gives you a three-dimensional structure of the whole artery. And then when you go back with a stent, you can place the stent in a really exact location and actually do and you don't really need to inject in the second time that you enter the vein. So it actually reduces some other unpleasant effects that happen. So, and they're using our techniques. Okay. In the last 10 minutes that I have, I would like to briefly tell about another technique that is related somehow to the previous one. And this is a technique for measuring minimal geodesics. So what are minimal geodesics? First of all, let's start from the notion of distance. Say that I throw this stone into a pond. When this stone hits the pond, it creates these kind of ripples around its entry position and around its hitting position. Okay? If I pile these round circles, one on top of the other, which means that this axis now is the time axis, then I get something that I call a distance map. Okay? This is the distance map from this point. Finding, for example, the minimal path between this point and this point is just puncturing this cone at this point and then gliding along the gradient direction. So it's a steepest descent process, which is yet another way of proving that the shortest line connecting 2 points is a straight line. We have an efficient way of computing distances. So on flat domains, it's called the fast marching method. It's due to Setyan, and there is a related work by John Titsiklis from MIT. As long as the coordinates are orthogonal, these kind of methods work. However, we have been able to extend it to non-orthogonal meshes and compute distances on non-smooth manifolds. So if you have, for example, this image, and you would like to find the shortest path connecting between this point and this point, where it's weighted, here and now introduce weights into this game, then I have to solve an equation which is called the iconal equation. It's a way of computing this cone, but now it's deformed according to this weight. And then gliding along the gradient direction, I extract these veins here. So first of all, I click here. I compute these contours, this deformed cone. Then I click here and I propagate along the gradient direction towards the source point, and thereby extracting these minimal geodesics. Now, these minimal geodesics are geodesics on a flat domain, which is isotropic but inhomogeneous, because at each and every point I have a different weight. And we can solve other problems like the shape from shading problem, which is the problem for constructing a shape out of its shading image. Navigation problem in many dimensions, and I will go briefly on other navigation problems. And the important tool that I would like to focus on is measuring distances. Now, think about your pond as being smeared on a smooth manifold. So this is my pond, and I throw the stone now at the tip of the nose here. These are the ripples or the equal geodesic contours that are being formed as this distance is propagating on this three-dimensional shape. So we have a relatively efficient way of computing the geodesics on a three-dimensional shapes. And now we have a set of applications and for that. So we can retriangulate surfaces, and we can segment manually objects out of by going along some weighted regions on this manifold. But the most important application, at least from my point of view, is the following. And this is something that I will talk about on Monday. Most of the organs that we look at are more or less isometric. What is isometry? When I think about the hand, for example, and I think about the distance between this point and this point, and I think about the geodesic distance, which is the distance on the hand, it doesn't really matter how I embed, how I place this hand, what is the pose of this hand in 3D. What is important is the distance along this surface. Now, the hand does not stretch or tear itself apart, or at least it does it in a really insignificant way. So I can say that this hand is isometric to this hand. The best example is a piece of paper. For example, this paper is isometric to this paper. It doesn't really matter how I embed it in 3D. So in order to match the first paper to the second one, or this hand to this hand, what I need to do is to measure all these geodesic distances and preserve and compare the set of geodesic distances between these two hands. Now, how to do it exactly, I will talk about on Monday. And we use this technique that we have developed in order to do face recognition. Now, face is not a hand. Face is something more complicated. So for that, we conducted the following experiment. We placed many points on the face of Eyal Gordon, who was the lab engineer at the time. And we measured both geodesic distances between points as well as Euclidean distances between points. So I measured the geodesic distance, which is the distance along the surface, as well as the Euclidean distance, which is the difference in coordinates. And now we created a histogram comparing the Euclidean distances as well as the geodesic distances and present their distribution. What we have seen is that Euclidean distances change a lot as we change our expressions, while geodesic distances, well, if the face would have been exact isometric, if the mapping between one face to the other would have been isometric, then we would have gotten a delta function here. However, it's not exactly isometric, so the geodesic distances are distributed more or less like, well, better than the Euclidean ones. So now it gives us a legitimate way of treating faces or facial expressions as isometries. Now, in order to compare two surfaces, two isometric surfaces, and this is also true for most of the human body. My shirt, for example, is more or less isometric objects unless I stretch it. My hands, all of my limbs are articulated in a sense, so I don't tear it or change its topology in any way. So it gives us a very powerful way of aligning two surfaces together, two isometric surfaces together. Very recently, we also developed a measure to compare two surfaces using something which is called Gromov-Haslov distance, and this also relates to a method by Guillermo Sapiro and Facundo Memoli, and we can compute it in a very accurate way. And again, I will talk about some of these issues on Monday. Let me go back and tell you that I was flattered by the fact that the book is here in the library at the differential geometry section, although it deals with images, and I take it as a compliment. Thank you for your attention.